Is the video ready? All right, so please start. Non-invariants from finite-dimensional integration.
Thank you. So first of all, the way I wrote the abstract, it was a bit tautological, and Rinat pointed it out. So I added the words perturbed Gaussians, and we'll see what they mean later. And now it's not at all tautological. So basically, I will tell you that you can associate a space to every node basically by multiplying low-dimensional Euclidean spaces for each edge of the node. And a Lagrangian, which is the exponential of a sum of one contribution from each crossing, and then it will be a perturbed quadratic, so a perturbed Gaussian Lagrangian, and then the integral of that thing will be a not invariant. And then questions and answers, are there such things? Answer is yes, that's what I'm going to talk about. Are they any good? Well, they turn out to be the strongest we know, the strongest not invariant we know per CPU cycle. Okay, computable. Of course, the strongest not invariant we know is the identity. Okay, didn't Witten come up with such things long, long ago? No, that was infinite dimensional, not rigorous. But integrals belong in analysis? No, ours are algebra. Okay, that's the abstract. I hope you all have a copy of the handout. If not, there are a few more over there. Thank you for having me in Groningen. There are a few further. This URL has a copy of the handout, and we'll have a link to the video and a few other things, so keep it in mind. I wish to thank my sponsors, so the NSERC and the Chu Family Foundation. And I should also say that what I'm going to talk about is fun, but it's not fully ready. It's like kind of, a lot of it is last minute work, so I apologize. And let's start. So I think you already know about knot theory and about invariants. But so let me just say, the good about knot theory is that it's at the center of low-dimensional topology, and the theory of invariants is an extremely rich theory that connects to almost everything. The agony is that 1 and 2 don't really talk to each other. So we don't have enough topological applications of these fancy invariants that come from fancy algebra. And also, if we were topologists, we would never discover these invariants. They were somehow discovered in algebra, not in topology. And I think it means that we're missing something. I think, to me, it means that's kind of the dogma that things come from from universal, quantized universal enveloping algebras and their representations, and then it is wrong. I think things come from somewhere more general, of which this might be the first example. But we don't understand the more general thing yet. So in that sense, my talk and Rinat's talk in the beginning are about on the same topic. I mean, he's also trying to go beyond the classical dogma. Now, am I offering a replacement? Not today, but I'm offering another perspective, and maybe if we will accumulate enough of them, we will finally understand what's going on. Anyway, and now let's start with content. And the content, I will call it the SL2 mod epsilon squared example, but I will not explain the name until much later. So let T be an indeterminate, so just some number, some variable, and let epsilon be something whose square is equal to 0. So perturbation parameter, but I'll only look at it modulo epsilon squared. Then, given a knot, now I want my knots presented in a specific way. So they have to be long knots. All the crossings have to be facing up. So it's oriented, and all the crossings must be facing up. And of course you can arrange that, because if you have a sideways crossing, you just turn it around, okay? you must number the edges. So 1, 2, 3, but then some edges will have rotation number. So many edges will go, straight from one crossing to the next without any rotation, but some will have a rotation numbers. Edges that have a rotation number, I will cut just before they enter the next crossing, and then they will carry two labels. So this edge carries label 4 and label 5, and there is a cut. And then 6, 7, and 8. And then I will denote the rotation number of those cut edges by phi sub the number of the edge. So phi sub 4 is -1 because this edge rotates once clockwise, and that's the negative of the mathematical convention for rotation numbers. Okay, now let's associate an integral to a knot presented in this way. So first of all, to every edge except the last, I will associate a two-dimensional space. So for the first edge, it will be R2 of the variables P1 and X1. For the second edge, it's R2 of P2 and X2, and then I'll multiply all these spaces, so I'll get R to the 14 overall. Okay? And then for the crossings, for each crossings, I will associate a little Lagrangian. So for this crossing, I will have a Lagrangian of the crossing. It's a positive crossing, and it's a crossing in which edge number 1 goes over edge number 5. So it will be the piece of the Lagrangian corresponding to x plus of 1, 5. Okay? And so likewise for this crossing and for that crossing. And then finally, there will be another piece of the Lagrangian for the edge that rotates, and this will be L C sub 4 -1 because the rotation is in the -1 direction. Okay? And then the invariant I will construct will be Z, which is an integral of the product of these calligraphic L's corresponding to the features of the knot, so 3 crossings and 1 rotation, integrated over a 14-dimensional space, as I said before, but the measure on the real numbers, I will take it to be 2 pi to the -1/2 times the standard measure, just to kill all the pi factors that will otherwise occur. And those L's are given here. So calligraphic L of a crossing is t to the sine of the crossing over 2 multiplied by the exponential of just ordinary uppercase L. And calligraphic L of a rotation is t to the rotation number over 2 multiplied by the exponential of a Lagrangian of an uppercase L, where uppercase L and of the crossing and uppercase L of a rotation number are given by these formulas. These are awful formulas. I acknowledge that. They look terrible, but they do good things, so please bear with me. Okay, so what are the formulas? So the Lagrangian for a crossing is the x variable at that crossing multiplied by the pi plus 1 minus pi, where pi plus 1 and pi are the variables associated with the p variable of the next edge, and pi is the p variable of the ith edge. And plus xj, well, basically I don't have much to say except it's an ugly formula. So it has a first part which is quadratic in the x's and the p's, and a second part which is of a higher degree, but it's multiplied by epsilon, so you can think of it as a perturbation. And similarly for the Lagrangian of a rotation. So I multiply all of those calligraphic L, which is the same as adding all of those lowercase l. And in the case of the trefoil, as before, you find that the value of the invariant, I'm sorry about that, it's a bit off center, is the integral over 14 variables of the Lagrangian of the trefoil. And this Lagrangian is the sum of the red contribution, the green contribution, the blue contribution coming from the red, green, and blue crossings from before, and the purple contribution coming from the rotation, and these are the contributions. Okay? Now, if you look at this Lagrangian a little bit more closely, and if you are familiar with physics, it turns out to have a part which looks a little bit like kinetic energy in phase space. So it's x times p dot, or x times, so it's discrete quantum mechanics in phase space. Okay? And then it has a contribution which is not yet multiplied by epsilon, but it is multiplied by t minus 1, and often I think of t as being a number near 1, so t minus 1 is kind of small. So there is some non-local kinetic energy perturbation, correction, and then there is a perturbation, a messy perturbation. Anyway, whatever it is, you compute this integral, and I will show you a little bit in a moment how you do it. And the result comes out to be the formula written here, which you can read out as the Alexander polynomial to the minus 1 multiplied by the exponential of epsilon times some constant divided by the Alexander polynomial, sorry, this should have been squared, not minus 2, times rho 1, where rho 1 in fact was mentioned in Jorge's talk. Okay? And it's also known as the Rosansky-Overbay polynomial. And then theorem, Z is a not invariant. I haven't yet told you how to compute it, but I can tell you the key point already for how to prove that it is an invariant. To prove that it is an invariant, you need to show invariance under the 3 Reidemeister moves. Not quite, because you also have to worry about rotation numbers, because I've included rotations as a part of my features. So really there are sort of 5 Reidemeister moves, which include the ordinary Reidemeister 1, Reidemeister 2, and Reidemeister 3, but also some things that have to do with rotation numbers. Don't worry about it too much. The point is, you want to prove that the integral for the left-hand side is equal to the integral for the right-hand side. You use Fubini's theorem to integrate, to carry out first the integral over the variables that appear here, and then over all the other variables. And then you just show that the local integral that corresponds to just this part is equal for the 2 sides. That's the sketch. Okay? Once you know how to compute such integrals, the proof becomes mechanical. At the moment, we still don't know how to compute such integrals. Anyway, so now the to-do list for the rest of the talk is to explain that the formulas are human awful, but actually computer extremely easy, and in fact can be computed in polynomial time. Then I have to tell you that this is a very strong invariant. Then I will tell you the details of the proof. I will actually carry out the proof. Then I will say a word about where is it coming from, because it looks like it comes from outer space. It doesn't. And then I want to make a philosophical point, again connecting with Jorge's talk, that universal invariants, and this is more or less an example of one, are qualitatively better than the one coming from representation theory. So let's go for it. So first of all, how do you compute Gaussian integrals or perturbed Gaussian integrals? So suppose my goal is to compute integrals of the form, the integral over Rn, like r to the 14 in the example, of and the measure is of course with the pi's divided, of the exponential of an arbitrary quadratic plus a perturbation, which will generally speaking be a polynomial in the variables. And let me pretend that it is convergent. So either the quadratic is positive definite, so its negative is negative definite, or it's imaginary. And later I will ignore the convergence issues. Okay? So people who do quantum field theory know this very well. Many mathematicians don't. I'm going to show you how to do it, but it's a presentation that people in physics don't know. It's slightly different than the usual presentation. I think the main reason for that is that I'm a weirdo and I like weird things. Okay? No, it's also a bit cooler, I think. So let me let me define z sub lambda of x. So I'll introduce a parameter lambda, and let me define z sub lambda of x to be some normalization factor times the same integral, but with the x in the perturbation replaced by x plus y. Sorry, the integral is integral dy, so now I have a free parameter x, okay? And I'll also divide the quadratic form by lambda. Now, z sub 1 of 0, so if you set the x's to 0 and lambda to 1, if you set x to 0 and lambda to 1, this is the same integral except with the variables changing their name. Z sub 0 of any x, so if you set lambda equal to 0, well, you can't quite set lambda equal to 0 because you divide by lambda, but you can take the limit as lambda goes to 0. As lambda goes to 0, you get here, this quadratic term explodes and converges to a delta function. And the normalization factor was arranged so that it really is a delta function, and it's a delta function at y equals to 0. So you simply get the exponential of v to the x, again, times some normalization, the determinant of the quadratic form to the minus 1/2. That's all easy. And then, if you let Gij be the inverse matrix of the matrix defining the quadratic, then you derive a differential equation. The differential equation says that the derivative with respect to lambda of this new quantity is, roughly speaking, it's Laplacian with respect to x, where x is this variable, the new variable that I've introduced. So not quite Laplacian, because it's Laplacian where the derivatives are coupled by the inverse quadratic. Let's look at it very quickly, without detail. So apply the Laplacian to z sub lambda, and I'll do something funny. I'll write dx as, so dx goes into the integral, so I'll have dx apply, so this is dx and that dx. But then I'll subtract from each dx a dy. But you see, the integral of a derivative is 0. Because that's the fundamental theorem of calculus. Over the real line, if you integrate the derivative of a function, you get 0. If this was an integral, a convergent integral to start with. So this is equal to that. Now, dx minus dy acting on vx plus y gives 0, so I can ignore its action on vx plus y. And acting on the quadratic form, only the y's act. So I can differentiate very easily. I get this formula, then I look at this formula more closely, and I find that I can simplify it a little bit, and the bottom line is that it's equal to the derivative with respect to lambda. And so again, this is a verification that you can do, okay, you can check. But the point is that you get this heat-like equation. And then the solution is, well, from the perspective of lambda, it's a linear equation. It's the derivative with respect to lambda of a function is equal to an operator acting on that function. So the solution is e to the lambda times this operator acting on the initial condition, and the initial condition is the exponential of Vx. So the solution is that z lambda of x is this determinant to the minus half times the exponential of the Laplacian with coupling with coefficients g and j acting on v of x. So again, if you've been to physics, you're back to familiar grounds. This is stuff that every physicist knows. Anyone doing quantum field theory has seen this, and this is where Feynman diagrams are born. So basically, how do you evaluate z lambda of x? You expand the exponential, so the exponential is 1 plus v of x squared divided by 2, and then you differentiate with respect to the x's here. But differentiating means pairing the derivatives with respect to x here with the x's coming from here. And then when you think of the v's as the vertices, you think of the g's as the edges, and this is somehow how Feynman diagrams are created. This is all lovely. I want to do something slightly different. So from the perspective of physics, I want to switch to connected Feynman diagrams. So what I'll do is I'll define, instead of calligraphic lambda, z, this will be uppercase z. So uppercase z will be the log of calligraphic z. I guess the point is that I don't want to know the integral, I want to know the log of the integral, because my goal will be to integrate again, and I know how to integrate exponentials, or I'm learning how to integrate exponentials. So you set uppercase z lambda to be essentially the logarithm of calligraphic z lambda, and you substitute it into this equation, and you get a new equation, which is again an ordinary differential equation in lambda. And it's the equations of the derivative with respect to lambda of z lambda is equal to sum over ij over ij of gij, the inverse quadratic, multiplied essentially by the Laplacian, and then a nonlinear term, dxi z lambda times dxj z lambda. It's lovely to interpret this in terms of connected Feynman diagrams, but that's not the point. That's not what I'm going to do right now. That's not today. And then there is also an initial condition. Very clearly, z0 is v, because calligraphic z at 0 was exp of v. So z0 is v. Now, how do you solve a differential equation? It's actually, from the perspective of lambda, it's an ordinary differential equation. The derivative with respect to lambda of z lambda is equal to some operator applied to z. So how do you solve it? Well, you solve it in the same way that you solve ordinary differential equations in an ordinary differential equation or differential equations class. You use Picard iterations. So, in general, Picard iterations tell you that if you want to solve d lambda of f of lambda is equal to an operator f applied to f sub lambda, then you start with f sub 0, which I'm assuming is given, and then you iterate the operation f goes to f0 plus the integral from 0 to lambda of the operator applied to the function, applied to the previous iteration. So you basically iterate this again and again and again, and eventually it hits a fixed point, or it approaches a fixed point, and the fixed point is the solution of the equation. In our case, you can check that the solution is reached after finitely many iterations. So now, you think all of this was heavy duty, or not heavy duty, but you think it was integration, you think it was analysis, you think it was solving differential equations, but given the finiteness, it's just pure algebra. Differentiating polynomials is an algebraic operation. Integrating polynomials is an algebraic operation. And if you only need to go finitely many times to get to the limit, then you go finitely many times, and it's been algebra all along. So this is a completely algebraic definition, despite its look. So I define Gaussian integration, integral with G. And in fact, if you remember when I wrote the definition of the invariant, I used integral with G. So I define it to be the result of this process, ignoring whether or not the original integral converged. I don't care. Okay, it's still it's a definition that makes sense. Now, it turns out to have all the formal properties of integrals. For example, and what I care about the most, it has a Fubini theorem. Why does it have a Fubini theorem? Well, we could crunch through the definition and see that it has a Fubini theorem. But in fact, Fubini's theorem is an algebraic equality. It's an equality between two things that are defined algebraically, and it's true on some part of the parameter space. It's true for some integrands. It turns out that it's true on a Zariski dense set of integrands, so therefore it's true always. Okay? So this is the definition of, this completes the definition of the invariant. Now, sorry, this is me. I mean, I can't talk without implementing. All of this is actually runs on the computer. So here's a quick implementation. If you want the full, if you want the Mathematica notebook in which this implementation is available, it's on omega epsilon beta defined before /AP. So I first load some standard knot theory packages for use later. That's not interesting. That's not part of the integration. And then I define what does it mean to bring an expression to a canonical form. This is basically, the key word here is probably here, factor. I like to see my polynomials factors. Other people may like them expanded, but this is, okay? And all the rest says, basically, you factor the coefficients with respect to t, and all the rest stays unfactored. So that's the way I like to see my polynomials. It's not particularly interesting. Now comes the key point. Here is the definition of integration. So the key point, this is the full definition of how to integrate. So first of all, I unprotect the command integrate because it's a protected command in Mathematica, and I'm going to overwrite it. So, and then I define the integral of a scalar times e, so the exponential of a Lagrangian, d, a list of variables, to be a module with local variables. And the key points within this short definition is, first of all, I make the quadratic form be a table of the partial derivatives with respect to the variables of the Lagrangian. Then, if the determinant of the quadratic form is equal to 0, well, then my whole procedure crashes, right? Then I cannot invert the A matrix, so I cannot get the G matrix, everything crashes. So then I return an error message, the degenerate Q, and quit. And otherwise, I define Fz, this is the operator, to be 1/2 times exactly the summation that was written before, that I derived before, and then I ask the computer to find a fixed point of the iterative process, again, the Picard iterative process, and then I output, and this should happen in after finitely many iterations, and then I output the result into which I substitute lambda is equal to 1, and all the variables are set to 0, because this was the, that was the procedure. That's how we computed Gaussian integrals. And then I protect integrate once again, just to leave the subject, leave the ground untouched. Okay. Anyway, let's check it. So this actually runs. If you, the human, type in to the computer, please compute the integral of a Gaussian, but actually, let's compute its Fourier transform. So let's add, this is like the perturbation term. This is an added thing. So let's add I times psi times x. The program runs. The program is good enough to compute this, and it outputs a Gaussian with the inverse quadratic. So if you know something about Fourier transforms, that is the Fourier transform of a Gaussian. Then let's do something fancier. So let the Lagrangian be a general quadratic form in two variables. So the quadratic form in the variables x1 and x2, given by the matrix A, B, B, C, it has to be a symmetric matrix. So it's just -1/2 times x1, x2 dot this matrix dot x1, x2. And for good measure, let's take the Fourier transform, so psi1, psi2 dot x1, x2, except I made a mistake and forgot the I factor, so it's not the Fourier transform, it's the Laplace transform. And then let's ask the computer to compute this. So the Laplace transform of an arbitrary Gaussian into variable, the computer outputs this. It's not particularly interesting, and that's actually not what I wanted to show you. What I wanted to show you is that now I can integrate the same L, but with respect to only one of the variables, and then test if the thing I computed before is equal to the integral of the result of z1 with respect to x2. So basically I'm testing Fubini. And the computer tells me that z1, the result of the integral, or the integration with respect to only one variable, is equal to this. If you look at this formula, it only depends on x2, because x1 was integrated. And the result for this equality is true. So, yes, Fubini holds. Let's do another fun example. Oh, I should have told you that there are also hacks in the program. The program is lovely, but there are also hacks. So a good program would not depend on the environment. But, I wanted to fit it in one page, and I didn't want the notation to be cumbersome. So I made the program know that there is a special variable called epsilon, which is the perturbation parameter. So, for example, when I compute the quadratic form, I first set epsilon equals to 0 in the Lagrangian. But then another hack is that I included something called $pi. $pi is a projection. It starts as being the identity. You don't project. But later it will become project subject to epsilon cubed is equal to 0, or epsilon to the 13 is equal to 0. So basically project to power series which go only up to degree 12. Okay? And now in the example, I finally set $pi to be projection modulo O of epsilon to the 13. And then I compute the so-called phi cubed theory, the integral of a Gaussian perturbed by a cubic perturbation, and get the answer as a power series in epsilon. The computer outputs that the power series is the exponential of 5 epsilon squared divided by 24 plus blah 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 blah. You want to know what this series is. You take the list of numerators or denominators, but I did the numerators. So 5, 5, 1105, 565, 82825, whatever. And you punch it into Google. And Google immediately recognizes that this series appears on a website, namely on the online Encyclopedia for Integer Sequences. And over there, it appears as the numerators of the mass formula for connected vacuum graphs on 2A nodes for a phi cubed field theory. So, fancy name, but we've just computed it. Okay? So now we got to trust our program, and we started applying it to the things we care about.
Sorry?
So, yeah.
You said phi-3 theory should have maybe finite dimensional phi-3 theory?
Oh yeah, one-dimensional. One-dimensional.
Okay.
Yeah. I mean, here it's a one-dimensional integral, a single phi. It's not phi to the fourth that they teach in quantum field theory classes, which is awful. Okay, it's just the one-dimensional analog.
Yeah.
Okay. But now that we only care about finite dimensional integration. So now that we trust our program, I let K be the mirror of the trefoil node, because in fact the trefoil node I wrote over there is the mirror of the one that the database knows. And I asked the computer to print the features of K. I didn't show you how the features program runs, but this is not interesting. This is sort of basic node theory. So the features of the node K is that it has 7 edges, actually 8, but the last one I don't care about. And it has a rotation number of -1 on edge number 4. It has a positive crossing in which edge number 1 goes over edge number 5, and so on. So now that I know what the output would look like, I implement the Lagrangian. So I tell the computers that the Lagrangian for a crossing of sign S in which edge I goes over hj is t to the s over 2 times the exponential of, and this is, I hope, the same formula as the formula I wrote on the first page, likewise for rotation numbers. And for a knot, the Lagrangian is simply the product of all the Lagrangians for all the features. And I also wrote a little program that tells me what are the variables for a knot. So the list of variables is a table as I goes up to the number of edges of pi and xi. So for example, for the node K that we just looked at, maybe I should make so for the node K that we just looked at, the list of variables is p1, x1, p2, x2, and so on up to p7, x7, and the Lagrangian is written here. And then again, it's awful, but I don't want to ever look at it. The computer looks at it. I'm asking the computer to compute modulo epsilon squared, the integral of L of k d, the variables of k, and the computer outputs exactly what I said it would, with an extra factor of I, which has to do with some signs that we messed up with. Okay? Now, so this program is more or less a demo. And then we have a faster program, and it's available at this reference. And we've computed this invariant for all nodes with up to 14 crossings. And just as Jorge said, it's stronger than the pair Humphrey polynomial and Jovanov homology. Stronger in the sense that it attains more distinct values. Okay? Also, in as much as we know, this invariant, namely the Alexander polynomial in row 1, is the strongest knot invariant that can be computed in polynomial time, and hence even for very large knots. So this program again is a demo, but the other program can compute it for knots with 100 crossings with no particular difficulty. Okay? So why is it polynomial time? Let me just say it very, very briefly. Basically because, okay, how do you compute such an integral? First of all, you invert the quadratic form. Right? This was one of the key points in Gaussian integration. You invert the quadratic form. The quadratic form is n by n. If the knot has n crossings, so for our knots it's 2n by 2n, so 14 by 14. So the quadratic form is essentially the size of the knot, multiplied by some constant. Inverting a matrix with Gaussian elimination is a polynomial time operation, and furthermore, there are programs that do it extremely efficiently. After you do that, you look at how to compute integrals, but our integrand is the exponential of this thing. It's an exponential of a series in epsilon, and I only care about it to epsilon to the power 1, or maybe later I will care to epsilon squared. But if I only care to epsilon to the power 1, then basically the exponential of this series is just the sum of the contributions in it. The contributions are localized to the crossings. So the computation is going to be a sum over crossings, or if I go to epsilon squared, it will be a double sum over crossings, but that's still polynomial amount of computation. And then for each crossing, I have to compute just the integral of, let's say, the red contribution. And this amounts to pairing the x variables with one side of the quadratic and the p variable with the other side of the quadratic in all possible ways. I don't know how many ways there are to do it, but it's a finite number for each crossing. So it's a finite amount of computation for each crossing, and then it gets summed over all the crossings. So it's a polynomial time computation overall. Again, I didn't give details, I just gave the spirit. Okay. And now let's prove, I claimed the theorem, let's prove it. So let me show how you prove invariance under Reidemeister 3. So I need to show that the integral for the left-hand side is equal to the integral for the right-hand side. In principle, this Reidemeister 3 occurs within a big knot, so the entering left edge here will have a label, let's call it I, and then the next edge will be I plus 1, and then the next edge will be I plus 2, and likewise j plus 1, j plus 2, and likewise on the right. And here is the thing, like edges I, j, and k attach to lower crossings. So they may, so the variables xi and pi, and xj and pj, and xk and pk may get contributions from the crossings below, because they might be, so this I might be the j plus 1 of another crossing. And if you look at the Lagrangian, it has, where is the Lagrangian? Maybe I shouldn't do it. Maybe I should do it by scrolling. Right? If you look at the Lagrangian, it has contributions with plus ones in them. So, okay, likewise, these variables, the top variables, are the bottom variables of whatever appears above. So so the thing I can be confident about is that the middle variables are not touched by anything else. So what I'll do is I'll take the Lagrangian for the sum of the Lagrangian contributions for these three crossings and integrate it with respect to only the middle variables. Likewise, on the right, I'll get functions that depend on the variables on the bottom and on the variables on the top, right? Because these are not integrated upon. And if I'm lucky, the two functions will be equal. Oops, I'm not happy. I'm not lucky. So the left-hand side is the integral of the Lagrangian for a product of three crossings. This is exactly what you see on the left here. With respect to the middle variable, only the plus one variables. And the right-hand side is the integral corresponding to that with respect to the plus one variables. I'm asking the computer whether the left-hand side is equal to the right-hand side, and the answer is no. So unfortunately, the proof fails. But now I look again at the Lagrangian, and I see that the Lagrangian of a crossing has xi and pi plus 1, but not xi plus 1. So in fact, the x variables, xi, xj, and xk, are not going to be touched. They are never the plus 1 of the crossing below. So I can integrate with respect to the x variables too. So here is again the same Lagrangian, but now I integrate it. Instead of with respect to the plus 1 variables, I add xi, xj, and xk. And this is the left-hand side. The right-hand side is the same for the right-hand side. I'm asking the computer to print whether left-hand side is equal to right-hand side, and the computer says true. So I'm happy. I'm happy until I look at the details. So I'm asking the computer to actually print the left-hand side, and the left-hand side is degenerate quadratic. So the two sides were equal because they produced the same error message. That doesn't work. That's not great. Okay? So take 3. Now I say, okay, I still want the same thing. I still want to say that this function is equal to that function. This function is a function of the top. These functions are functions of the top variables and of the bottom p variables, because the bottom x variables I plan to integrate. Maybe the two functions are equal, just our programs doesn't know how to integrate them because it's not a Gaussian, because the quadratics are degenerate. So instead of computing the functions, so instead of computing this as a function of the p variables at the bottom, I compute the Fourier transform with respect to the p variables of the bottom, at the bottom. But computing the Fourier transform adds integration. The Fourier transform is an integral. So the integrals become same integrals as before, except I'm adding these I pi I pi, I pj pj, and I pk pk, pi k pk, and this makes it a Fourier transform. And now I also integrate with respect to the p variables, the variables of the Fourier transform. And if the two Fourier transforms are equal, the two functions were equal, and I'm good. And the computer prints the answer true. And again, you shouldn't be so confident because we made a stupid mistake before, so let me print the left-hand side. The left-hand side looks like the disaster that it should look like, and if you look at it more carefully, it's just the right form. And so now I know that it's invariant under Reidemeister 3, and invariance under the other Reidemeister moves is proven in a similar way. I should have asked before, questions, comments? So again, yeah?
Yeah. So isn't this calculation equivalent to the calculation in the other two takes on the invariance on Reidemeister 3?
No.
Do you know what's different? Why do you know the first one comes out with an error?
So, okay, the first one, I just didn't integrate enough variables. I had the freedom to integrate, take one. I had the freedom to integrate over another variable, and I didn't. So the two Lagrangians before any integrations are obviously different. Before any integration are obviously different. And then you try to integrate as much as you can to make them equal.
So from our appearance they would look equal, but Mathematica doesn't see them as equal.
Sorry?
From our appearance they would look
No, so the first attempt, they're just not equal. I just didn't integrate over enough variables. I could integrate also the bottom x variables, and I didn't. And as functions of the bottom x variables, the two things are different. It's only after I integrate these variables that they become equal. So this false is a genuine false. The second true is actually a genuine true, except it was obtained by false methods. Namely, the computer doesn't know how to carry out this integral. Okay? And it printed true because it was saying, I don't know for both sides.
Yeah.
And then to make it know how to do the integral, I add yet another, I do this Fourier transform trick.
Do you have any understanding why in the second take it produces an error?
Oh yeah, of course. I mean, if you look at the Lagrangian carefully enough, it's kind of clear that it's degenerate, that it's not Gaussian. If you basically, it becomes, the x variables and the p variables are paired with each other, and if you integrate more x's than p's, or more p's than x's, the result is going, the Lagrangian is the quadratic form is degenerate. And you can see it, but this is something that the eye can see.
Yeah, okay. Yes, thanks.
Okay? Right. So again, I want to emphasize, it's a complete mess from a human perspective. But from a computer perspective, this is an extremely efficient and powerful invariant. Okay. As for where is it coming from, I think the most honest answer is we don't really know. So we know how we came to it, but that's kind of our funny, convoluted personal history. It's not, it's not how I would like to teach it to undergrads 20 years from now. Okay? And in a way, it's good because maybe there is more where it came from. In fact, we know that there is more where it came from. And we got to it from something has to do with Lie theory, but it's kind of hard to imagine that Lie theory will be necessary, that you will end up seeing Lie theory by looking at these crazy integrals. So maybe it's coming from somewhere else, and that's what I'm seeking. I kind of expect that we will have more, I hope that we will have more than Lie theory. Anyway, the personal answer, how this came about, is from Lie theory, and I can outline it very, very briefly in the next few paragraphs, in the next few slides. But I should also say that we were lazy. We didn't really derive it from Lie theory. We only derived the pattern from Lie theory, and then we fixed the constant by playing. Okay? So, so what's the Lie theoretic story? And again, I'll be very brief. Well, partially because there is no time, partially because people here perhaps know it already, especially Jorge. That's part of his thesis, okay? So basically, so first of all, there is a bijection between morphisms and generating functions. More specifically, if you look at morphisms between one polynomial ring and another polynomial ring, then, well, the dual of a polynomial ring is a power series ring. So hom this to that is the dual of that tensor that. So it's a power series ring tensor the polynomial ring, and that's just a ring of power series in one set of variables, the variables dual to the variables of the x's here, and which are also polynomials in the second set of variables. So that's the generating function construction. So every morphism between polynomial rings has a generating function. Now, many relevant spaces in algebra are secretly, as vector spaces, polynomial rings. So universal enveloping algebras, quantized universal enveloping algebras are, by the PBW theorem, isomorphic as vector spaces to polynomial rings. So, so many morphisms that we care about in quantum algebra say the morphisms that defines multiplication from a quantized universal enveloping algebra to itself. All of these morphisms have generating functions, can be summarized by functions. Now, if you, in this language, composition becomes integration, yes?
So, just to make sure, like in this isomorphism G over there, the part in double brackets or our series should go to the right.
No. Oh.
Are you sure? I think so.
What should go where?
So the part in double series, in power series should go to the right.
Oh, yes, you're right. You are right. Sorry, I messed up.
Yeah.
I'm sorry. Thank you. Anyway, but it's your exam, not mine.
You can ask this tomorrow.
So, composition is integration. So basically, if you have a function from a morphism, again, a linear morphism, not a ring morphism, from the polynomials in x to the polynomials in y, and then another one from the polynomials in y to the polynomial in z, and you want to know what is the generating function of their composition, the answer is, loosely speaking, it's a Gaussian integral. It's the integral of f times g multiplied by e to the y dot eta, where eta is the dual variables to the y's. Why so? Gaussian integration becomes pairing with the quadratic, so you have to pair the y's. You end up needing to pair the y's here with the y's in g, and the etas with the etas in f, or maybe it's the other way around, sorry. And that's exactly what composition does. So that's the second point. The third point is, do not represent. Stay with universal enveloping algebras. And then the last point is that, and this is a bit hard, but for some specific universal enveloping algebras, not all of them, the generating functions you get are Gaussians, or perturbed Gaussians. And then if you add up all of these things together, you find that, okay, so quantum invariants are big compositions of many tensors. All of these tensors are perturbed Gaussians. Composing is integration against another Gaussian. So overall, you're left with Gaussian integration. You follow this very carefully, and you realize that for SL2, you're going to need two variables, x and p, and the form is roughly the forms that I wrote, and then you play with the constants until it works. And that's the end of the story. I don't know if I should, no, I'm over time, so I'll stop. So thanks again for having me.
Questions?
I have two questions. So first, when you're verifying the invariance of the Reiner-Meister tree, I didn't understand why there was like a choice of like integrating more or less variables. Like, isn't it just, why did you like try to integrate with fewer variables first and then that didn't work?
So, okay. This produces a function on r to the 2 variables times 6, so r to the 18.
Right.
Okay? This is a function on r to the 18. This is another function on r to the 18. If the two functions were equal, then their integrals would be equal. I'd go home happy and cheerful. Okay? So I should have started with testing if the two functions are equal. They're not equal. Okay? But, you see, at the end I don't care about their function, these functions. I'm going to integrate them inside like a 108-dimensional integral, right? Like I'm going to have a knot with God knows how many crossings, and it's going to be an integral over r to the 8. So I'm going to tell myself, let me first integrate over the, since all of these variables are going to be integrated over at the end, let me start by integrating the middle variables. If once I integrate the middle variables, the two things were equal, I go home happily. Okay? And so I try that. It fails.
It doesn't work. Okay.
It doesn't work.
Yeah.
So then I'm saying, I can't really integrate over the bottom variables. I can't integrate more at first thought. Because the bottom variables may be influenced, may be involved in the Lagrangians for the crossings below. So I can't integrate over the bottom variables. But then I look more carefully and I say to myself, in fact, the x variables are not going to be involved. I look at the actual Lagrangians, and the x variables are never going to be affected by the other crossings. So I can integrate the x variables, except I can't, because the computer doesn't know what to do.
Yeah.
The p variables, of the bottom p variables, I genuinely cannot integrate. I really have to show equality of functions, not of integrals. But then I do something tricky. Instead of showing equality of functions, I show equality of Fourier transforms. And Fourier transforms just mean yet another integration, and then the integrals become balanced, and I get, and then the proof works.
When discussing the Lagrangian, you notice the relationship with physics, and it looks like kinetic energy, at least the epsilon is 0 part. But you say that x times p dot looks like kinetic energy, but isn't that x dot times p? normally speaking? Because it's normally it's mv squared.
Oh, sorry. I don't even make the distinction. There is integration by parts,
Okay.
right? The integral of x dot p. So I mean, where is it? Sorry, that's a long way back. The integral. Oh my God,
That's
it's a
what
very
the
long way
is.
back.
When
Here.
you said the.
What am I
Slightly
doing?
further
Sorry.
back.
So the quadratic part, this, right,
Yeah.
is summed over from from I goes from 1 to 7. So by summation by parts, it can be written as pi times xi plus 1 minus xi, and then boundary terms.
Okay.
Or, you know, if you make the analogy with integrals so that it will look like x times p dot, then by integration by parts it's the same as x dot p. Yeah.
Yes. Do you have an explanation about the perturbated part? There's only one part. How is there any physical sort of?
Nope.
Okay.
I mean, I acknowledge it, right? It's I say at some point, where is it coming from? The honest answer is that we don't know. The dishonest answer is, you know, from a long and torturous process starting with quantized SL2. But hopefully there is a better answer, and we don't know it yet.
Yeah. Let's hope. Thanks.
So
Yeah.
you said that this code is a demo. So what's different from this demo code and the real one?
There was zero concern for efficiency. This is the zero concern for efficiency. No, but there is more. Roughly speaking, the code that we wrote follows this procedure for computing Gaussian integrals, and it means it assembles all the Feynman diagrams in real time. Like as it computes, it assembles all the Feynman diagrams. But you can pre-assemble them. If you know what they will look like, you can pre-assemble them and then just compute each one, and then it's much faster. And that's the other code, essentially. I'm being a bit loose. Okay, you know what? Let me be even more honest. The even more honest answer is that I didn't fully analyze the code. Okay, so the code was not written for efficiency, and I didn't go through it line by line to check why is it slow, because I don't care, because it was meant as a demo. Yes.
So where did you use the knottiness of this knot? Why not a link here? It was a long knot, but what was wrong?
Nowhere. That's also a link invariant.
Just integrating out over a link diagram. But it
Okay.
still needs to be long, or not?
Link or upward tangle?
Sorry.
like-
So it's a cut link invariant. So it's a link invariant of links with one cut. Sorry, I hope I'm not telling you a lie.
But for split links, Alexander.
Yeah, so
Yeah.
so it's not fully defined because the quadratic will sometimes be degenerate.
Right.
For knots, the quadratic will always be non-degenerate because this term is always non-degenerate, and the other term is relatively small,
Right.
meaning is small when t is set to 1, is near 1. For links, the first term will be degenerate, and so you will be dependent for the non-degeneracy on the second term, and it's a hit or miss. And
Right.
in fact, it's a okay. So I'm speaking. We haven't tested it, as you know, but comparing with experience from the other formulation, we know exactly what Rinat said. So if the Alexander polynomial is not equal to 1, this is going to be non-degenerate, and then it's an invariant of links.
Right.
But can you prove that it is an invariant of links? Like, because you can cut it open anywhere.
Sorry, not of links, of cut links, of links with one distinguished component which you cut.
Okay, but when I cut in another place, would then be
I don't know why it's the same.
okay.
Experiment shows that it's the same, but I don't know why it's true.
There is a theory of renormalized traces.
Right.
Yeah, but there are tools, we haven't applied them yet.
All right.
We're playing games. Sometimes we get things, sometimes we don't. It's your job, graduate students here, to actually succeed.
That's right. It's a good note to end on. So let's thank the speaker again.